In this video, I'm going to go through the third topic for our course, optimal risky portfolios. So what I have up here is that the investment decision can be viewed as a three-step process. The first step is security selection of individual assets within each asset class, and that's what we're actually going to do in this topic areas. We're going to talk about how we create a portfolio using the expected returns and the standard deviations of individual assets. The second step is asset allocation in the risky portfolio across broad asset classes. And the third step is capital allocation between the risky portfolio and risk-free assets. That's actually what we did in the last topic, topic 2. So, like I said, what we're going to do in this topic is we're going to, in the end, create a portfolio of risky assets, and we're actually going to do this in Excel, but using different techniques to determine the best risk-return relationship we can get by choosing among several different assets the correct weights of each of those assets in a portfolio. We're going to do this in 2 steps. The first step is this video, which is going to go through most of the notes for this topic. The last portion of the notes for this topic, however, I'll be going through using Excel because it's just easier, and that's that's one way that you would do this in its actual application. And you'll see why when we get there. The math gets to be too big to do by hand very well. So let's start here with diversification and portfolio risk. Diversification decreases firm-specific, aka unsystematic risk, and leaves market systematic risk. What are examples of firm-specific risk? What are examples of market risk? So a firm-specific risk is a risk that only affects a specific firm or a small group of firms. So in general, firm-specific risks would include things like product liability, product obsolescence, managerial malfeasance, in other words, managers not acting well, and regulation. Like an industry-specific regulation. I include that one because oftentimes people cite that as a market risk. However, a regulation on the production of beef, for example, in the United States, isn't going to affect the entire market. It's only going to affect beef producers. And so typically, while regulations is kind of a broad idea, individual regulations generally are not market risks. So a market risk is a risk that affects most, if not all, firms in the market. And some examples include interest rate risk, unemployment, inflation. Some other ones would include the overall economy in general. So if the economy is in a recession, that's going to affect most firms. They're not going to be able to sell as many goods. Their revenues will decline. Their profitability will probably decline during those times. Gas prices, if fuel prices go up considerably, that's something that most firms will be affected by, either because they have to ship products, they have to move people or things around, or even at the very least their customers will be paying more of their paycheck out to travel, and so they're going to have less money to spend on other things. So the idea of a market risk is that it's a risk that affects most, if not all, firms. And the idea of diversification is that we can, by diversifying, by combining unrelated assets, or assets for which the returns are generally unrelated, we can eliminate or get very close to eliminating firm-specific risk. So if one investment that you have, an investment in a company that you have, if that firm has something go wrong. So, for example, a few years ago, Chipotle had a problem with E. coli, bacteria in some of their food. People got very sick. It really hurt their stock. Now, if you only own Chipotle stock, you lost a lot of wealth as a result of that. However, a smart investor wouldn't do that. They would hold a diversified portfolio. And so that Chipotle, that investment in Chipotle, while the stock price went down and would have had a negative return for them, because it was such a small part of their portfolio, it really didn't materially impact the overall portfolio. In fact, in some cases, that the negative thing that happens to a firm, like in this example, Chipotle, is going to positively affect other firms. So, for example, people still want Mexican food. They don't want to go to Chipotle anymore because they might get E. coli and get really sick. So they're going to go over to Qdoba, or they're going to go to Taco Bell. And so their stock prices would actually increase as a result of, or at least their revenues and their cash flows would increase as a result of the problem with Chipotle. So again, the idea of firm-specific risk is that we can diversify away from it. The risk is specific to either the firm or a small selection, a small group of firms. Market risk is something that you cannot necessarily diversify away from. You can control it by choosing firms that don't have a lot of sensitivity to market risks, but you can't eliminate it because it is inherent in most, if not all, investments. So naive diversification is the diversification that occurs by just randomly adding securities to a portfolio. Think of throwing darts at a page of that lists a bunch of stocks. You're not trying to find the right stock. You're just guessing. You're just randomly choosing stocks. Efficient diversification occurs when securities are selected and the weights of the securities in the portfolio are selected to provide the lowest amount of risk for any given level of return. And that's what we're going to practice in this topic area. I'm going to give you a set of stocks later on, and you're going to calculate. I'm going to do it first with you, and then on your own you're going to calculate the best weights of those stocks in a portfolio to provide the best risk-return relationship. So naive diversification, just random. Efficient diversification, we're selecting the right securities to provide the best risk-return outcome. So we're going to start off with just a very simple example, a portfolio of two risky assets. For a portfolio of two risky assets, the rate of return on a portfolio consisting of a portfolio of bonds, which we're just going to call D for debt, and a portfolio of equity securities, E for equity, is calculated as follows. So the return for the portfolio is equal to the weight of our investment in D multiplied by the return for D plus the weight of our investment in E multiplied by the return for equity. And I have that explanation down here. The weights WD and WE, the sum, must equal to 1. So this represents all of our wealth. We're going to, in this case, choose between putting it in debt or equity. And really, it doesn't matter. We could call that investment 1 and 2, investment A or B. In this case, I just referred to them as debt and equity. But it doesn't matter what those investments are. There's nothing special about debt versus equity in this case. The expected return on the portfolio is equal to the weight of D multiplied by the expected return for D plus the weight of E multiplied by the expected return for E. So that's a pretty straightforward calculation. The variance of the two asset portfolio is, so the variance is the standard deviation squared. It's equal to the weight squared of D multiplied by the standard deviation squared, which is the variance of D, plus the weight of E squared multiplied by the variance of E plus, and so these two together would give us the weighted average. Okay. What this third argument does is it reflects the interaction or the relatedness of the returns for our two investments, D and E, and shows how that affects the overall variance. So if we're diversifying, our covariance will be negative. Okay, so if we're diversifying away some of that firm-specific risk, our covariance will be negative. Sorry, I spelled that. Diversifying, that's the word. Diversifying away firm-specific risk. The covariance will be negative. Sorry about that. Will be negative. And that's important to remember. If we have a positive covariance, that means they actually move together, and enough so that it increases the risk of the portfolio by combining them. We don't want to do that. At the very worst, we want that covariance to be equal to 0. Okay. We want that to be equal to 0 so it doesn't add additional risk to our portfolio. Our covariance is calculated as the sum of the probabilities of a scenario multiplied by the return for D minus the expected return for D multiplied by RE minus the expected return for RE. Don't worry about that too much. This is the calculation you want to know. So the covariance is equal to the correlation coefficient, and that is rho, the Greek letter rho, multiplied by the standard deviation of the returns for the first investment multiplied by the standard deviation of the returns for the second investment. So rho, the correlation coefficient, can range between -1 to +1. And for the purposes of diversification, we want this to be negative. Okay, we want rho to be negative. In other words, we want them to kind of move against each other, or at the very least not be related to each other. If rho is equal to 1, then we don't receive diversification benefits because they move together. The two assets move together. So the variance of the portfolio is equal to the weight squared for the first investment multiplied by its variance plus the weight of the second investment squared multiplied by its variance plus 2 times the weight of the two investments multiplied by their standard deviations multiplied by the correlation coefficient, and then to get the standard deviation we take the square root of the variance. So that's a lot of symbols. Let's do an example here. Consider a portfolio that is 50% invested in an equity and 50% invested in a bond. So we have our equity and our debt. Our correlation coefficient is -0.1, so they are slightly negatively correlated. They're not moving together, in other words, so we get a diversification benefit by combining these two assets. What that means in the end is that we improve our risk-return relationship by combining these two assets. So our annual average, so to calculate the return, we just take the weights. So the weight is 0.5 in equity and 0.5 in debt. So our return for our portfolio is equal to 0.5 multiplied by 0.2, and I should say this is the expected return for the portfolio, plus 0.5 multiplied by 0.10, which is going to give us an expected return of 0.15. Okay, so 0.5 multiplied by 0.2 is 0.1, 0.5 multiplied by 0.1 is 0.05, and adding them together we get 0.15. So our expected return is 15%. The variance of our portfolio, we're going to calculate that first, then we'll take its square root to get the standard deviation. So the variance of the portfolio is equal to 0.5 squared, so our weight squared, multiplied by the standard deviation of D, which is 0.2. 0.2 squared, plus 0.5 squared, multiplied by 0.4, and again I'm getting that right here, squared, just following this up here, plus 2 times 0.5, which is 0.5, so the weights, multiplied by 0.2, multiplied by 0.4, and we're going to then multiply that by negative 0.10. So let's just go through these different arguments and calculate them independently. So I'm going to take 0.5 squared times 0.2 squared, and I get 0.01. I'm going to take 0.5 squared multiplied by 0.4 squared. That gives me 0.04. Plus 2 times 0.5 times 0.5 times 0.2 times 0.4 times negative 0.1. And that gives me 0.004, or negative 0.004. So now I'm going to add those up, and that's going to give me my variance. 0.01 plus 0.04 minus 0.004 gives me 0.046. And so that's the variance of my portfolio. And then I'm going to take the square root of that variance to get my standard deviation. To be 0.214476, or 0.2145. Square root of the variance is equal to the square root of 0.046 is equal to 0.2145, or 21.45%. Right? So what I want you to see here is that the return for the portfolio is the weighted average of the return of the individual assets. However, and that's what we did here. We just took the weight multiplied by the value, 0.2, plus the weight multiplied by the value to get 0.15. If we did the same thing with the standard deviation, so we ignore the correlation between the two, the covariance between the two, we would have gotten 0.5 multiplied by 0.4 plus 0.5 multiplied by 0.2. We would have gotten 30% standard deviation. Okay, we would have gotten a 30% standard deviation, but because of diversification and that negative correlation coefficient, we actually reduced the riskiness of the portfolio relative to the individual assets. All right. So by diversifying, we'll get a better risk-return trade-off. So a common measure that we see in investing to measure the quality or the how well an investment is doing is the Sharpe ratio. I mentioned in class that I've been looking through and reading through different proposals from companies that want to help manage the retirement investment program here at Washburn for the employees. And this is a common thing that they use, that they showed us in our presentations on how they measure the quality of the investments that they choose. So the Sharpe ratio is equal to the expected return for a risky portfolio minus the risk-free rate divided by the standard deviation of that portfolio. So that's the Sharpe ratio. And then using the magic of calculus, I won't go through all the, proofing this, but this is what we end up with. Using the magic of calculus, we can solve the optimization problem by solving the following equation for the weights of the two assets. If we want to find the optimal weight in asset D, we would calculate the expected, and this isn't actually the return for D. Down here I say capital R sub D is equal to the return for debt minus the risk-free rate, and the return for equity, and capital R sub E is equal to the return for equity minus the risk-free rate. So for us, RD is equal to 0.2, so that's the expected, is equal to 0.1, and I'm just getting that from up here, minus the risk-free rate, and the risk-free rate we're going to use is actually 3%. So I'll go ahead and move that over to this next page. So capital R sub D is equal to 0.10 minus 0.03, which is equal to 0.07. And then capital R sub E is equal to 0.20 minus 0.03 is equal to 0.17. So going back to this equation, capital R sub D multiplied by the variance of E. So this is the return for D, this is the variance of E, minus the expected return for the equity, multiplied by the covariance of R sub D and R sub E. We're going to divide that by the expected return for D multiplied by the variance of E plus the expected return for E multiplied by the variance of D. So notice how we switch the two variances to different investments, minus the expected return for D plus the expected return for RE. And again, remember, this is 0.07 and this is 0.17, so we subtract out the risk-free rate multiplied by the covariance of RD and RE. This will be the same as the covariance for little rd and little re, because in both cases we're to get these two numbers, capital RD and capital RE, we're subtracting out a constant, and so the variability of those two investment returns don't change. We're just, because we're subtracting out a constant, it changes the value but not the variation. All right, so let's go ahead and calculate. We've calculated capital R sub D, capital R sub E. Let's calculate the covariance. So again, the covariance is equal to covariance of RD, RE is equal to, if we go back to the notes on page 1, we see that the covariance is equal to the correlation coefficient. So that's going to be negative 0.10 multiplied by the standard deviation of D multiplied by the standard deviation of E. So the standard deviation of D was 0.2. And the standard deviation of E was 0.4. So now we're going to multiply this through. We get negative 0.10 multiplied by 0.2 multiplied by 0.4, which gives us negative 0.008. All right, so now we have all the information we need to go ahead and calculate the optimal weight for D here. So the expected return for capital RD is 0.07. So the weight of D is equal to 0.07 multiplied by the variance of E. So we look at the standard deviation of E, it's 0.4. We're going to take 0.4 squared. And that's going to give us 0.16. So multiplied by 0.16 minus 0.17. And again, that's capital RE. So we get that right here. 0.20 minus 0.03 to get 0.17. Now I'm going to take the covariance of RD, RE, which we just calculated, as negative 0.008. And that's my numerator then. My denominator starts off the same way. 0.07 multiplied by 0.16. And again, I'm just taking it from here. Our second argument's a little bit different. It's going to be 0.17, so plus 0.17 multiplied by the variance of D. So the standard deviation of D is 0.2. If I square that, I'm going to take 0.2 squared. It's going to give me the value of 0.04. And then I'm going to subtract out the sum of RD plus RE. So the sum of those two is 0.17 plus 0.07. I'll just follow this, 0.07 plus 0.17. And then I'm going to multiply that again by the covariance of the two investments of negative multiplied by negative 0.008. Alright. So again, I just followed that equation for calculating the weight of D. So my numerator is going to be equal to 0.07 multiplied by 0.16 minus 0.17 multiplied by negative 0.008. So that's going to give me 0.01256. Divided by, so I'll take 0.07 multiplied by 0.16 plus 0.17 multiplied by 0.04 minus, open parentheses, because I'm going to add these two together, 0.07 plus 0.17 close parentheses multiplied by by negative 0.008, and that gives me 0.01992. And so this is going to give me the weight of asset 1, in this case we're going to call it debt, in our risky portfolio. So 0.1256 divided by 0.1992 is equal to 0.6305. Meaning that of our wealth, we're going to put 63.05% in the risky portfolio, and then the remainder, so WE is equal to 1 minus WD, so it's going to be equal to 1 minus 0.6305 is equal to 0.3695. So 63.05% of our wealth should go into asset D, and 36.95% of our wealth should go into asset E. And when we branch out, so again, the next step of this is going to be to branch out to multiple assets, more than two. So we'll look at 4, 5, even possibly 6 different investments that we're going to find the weights for. And as you'll see in that calculation, those weights are the ones that give us the best Sharpe ratio, the highest risk return, best risk return relationship. But for now, we're just going to look at the 2, and this is the most I would ask you to do by hand, is 2 different assets. I wouldn't ask you to go out to 3 assets, because it does get much more complicated once we get past the 2 assets, and you'll do the more than 2 assets using Excel in your first assignment for this class. So the last thing we want to do is to figure out, using our investment here, our risky portfolio. So our risky portfolio again is 2 assets, debt and equity, with the weights of 63.05% and 36.95% respectively. And now we want to figure out the proportion that we're going to put in that risky portfolio of a specific investor's wealth. So we did something like this in the last topic area, but now we've got a specific portfolio that we're going to assign this to. So assuming an A, or a risk aversion measure, of 3.5, what is the optimal weight in the risky portfolio Y asterisk in the complete portfolio? So remember, the complete portfolio consists of an investment in the risky portfolio and an investment in the risk-free asset. So now we're determining how much of this investor, who has a risk aversion measure of 3.5, how much of their wealth should go in the risky portfolio that we've created, and how much should go in the risk-free asset. So in this calculation, our expected return for the risky portfolio, we need to start off by calculating that. So E R sub P is equal to 0.6305 multiplied by our expected return for the debt, which is, if you look on the last page, it's 10%. On the previous page is 0.10, plus 0.3695, the weight of equity, multiplied by 0.20, gives us an expected return of 13.69, or 13.70%. 0.1370%. 0.1370 minus our risk-free rate. Our risk-free rate is 3%, minus 0.03. Now we have to calculate the variance of the portfolio. This is a little more complicated. If you go back in your notes, we've calculated it once already. So this is at the top of page 2. The variance of the portfolio is equal to the weight of D squared multiplied by the variance of D, plus the weight of E squared multiplied by the variance of E, plus 2 times the weight of D multiplied by the weight of E, multiplied by the standard deviation of D and E, multiplied by the correlation between D and E. And we know that that last argument there is the covariance. So let's go ahead and calculate this out. The variance of the complete portfolio, not the complete portfolio, the variance of the risky portfolio is equal to the weight of D squared, so that's going to be 0.6305 squared, multiplied by the standard, the variance of D, and so that's going to be 0.2 squared, or 0.04, plus 0.3695, the weight in E, so this is WD squared, this is sigma D squared, this is E, squared, multiplied by the variance of E. So 0.4 squared is 0.16. So this is the variance of E plus 2 times 0.6305 multiplied by 0.3695. So that's the weight of D, weight of E, multiplied by the standard deviation of both. So for debt, that was 0.2. So that's the standard deviation of D, 0.4, standard deviation of E, multiplied by the correlation, negative 0.10, coefficient, which again was rho d E. Sorry, this should be a sigma. Alright, so we've got that formula there. We can calculate our variance. So that's what I'll do here. .6305 squared multiplied by 0.04 plus 0.3695 squared multiplied by 0.16 plus 2 times 0.6305 times 0.3695 times 0.2 times 0.4 times negative 0.1. That gives us an answer of 0.0304, excuse me, 0.034 for our variance. And so our standard deviation of the, that's all I need to know. My variance down here of the portfolio. So my denominator is going to be 3.5 multiplied by 0.034. So 0.1370 minus 0.03 is our numerator, and that's going to be 0.107. And our denominator is 3.5 multiplied by 0.034 is equal to 0.119. And so our answer is 0.107 divided by 0.119, which gives us an answer of 0.899. All right, so now that we have the weight, the proportion that we put in the risky portfolio, which we created up here, the remainder, or about 0.101 or 10.1%, would go in the risk-free asset. So we would have Y is equal to 0.899, and 1 minus Y is equal to 0.101. If you want to go back to the last topic, then we could actually calculate the expected return. So the expected return on our complete portfolio is equal to 0.899 multiplied by the expected return for our portfolio here, which is 0.1370. Plus the weight that we put in the risk-free asset of 10.1% multiplied by that return. I apologize, I'm going off the page here. Let me write it down here. Plus 0.101 multiplied by 0.03, and that is going to give us an answer of 0.899 multiplied by 0.1370 plus 0.101 multiplied by 0.03. So our return for our portfolio is going to be 12.62%. Oh, sorry, 62%. And the standard deviation, remember that risk-free asset has no risk, and so it's just going to be equal to 0.899. We calculated the variance here at 0.034. So the standard deviation of the portfolio, and this is again the risky portfolio, is the square root of 0.034. Is going to be 18.44%. So we're going to multiply, since that's the standard deviation of the risky portfolio, we're going to take 0.899, our weight in the risky portfolio, multiplied by 0.1844. It gives us an answer of 0.1658. So the standard deviation of our complete portfolio is equal to 16.58%, and its expected return is 12.62. All right, so now that I've shown you how to calculate the in a two-asset environment, the optimal weights of risky assets, and then combining those with the risk-free asset to give us the complete portfolio, and then how to calculate the expected return for the complete portfolio and the standard deviation of the complete portfolio. Now let's go on beyond two assets. So let's go to the Markowitz portfolio optimization model. And this is where we're going to combine several different risky assets. And I'm going to show you a graph of this. I'm not a very good artist, so I found a graph online that really represents this well. But we have what's called a minimum variance frontier, and that's a graph of the lowest possible variance that can be obtained for any given level of expected return. The global minimum variance portfolio is the portfolio of risky assets that has the lowest variance of all risky asset portfolios. The efficient frontier is the range of all investments that are within the minimum variance frontier and are above or have a higher return than the global minimum variance portfolio. So let me pull in this this graph here, and I'll make this available online too. So we have a graph here of the kind of, and imagine that this is the possibilities for all different investments. Okay, so on the y-axis we have the expected returns, and the x-axis we have the standard deviations. And any point within this space, this entire space, could be a possible portfolio. So a combination of risky assets, and that can include a portfolio of one asset. So any combination of risky assets, we could find the risk-return relationship within this graph. So this is the global portfolio. Okay, any combination that you could make would be included in this area. So going back to the notes, the minimum variance frontier is a graph of the lowest possible variance that can be attained for any given level of expected return. So the lowest standard deviation for any given level of return. So that's actually going to be this entire line. Okay, this entire line is going to be the minimum variance portfolio or frontier. Okay. So the dark line and the dotted line here, that is the minimum variance frontier. Now, if I'm an investor and I'm an astute investor and I'm smart and I see all these different possibilities, what this means, what the minimum variance frontier means, is that for any given level of return, we won't find a portfolio that has a lower variance. Okay, so for any given level of return here, the best combination of assets will be along this curve. Okay. So I won't be able to find portfolios that are out here where my cursor is, because that provides me a lower level of variance or a lower level of standard deviation for a given level of returns. These wouldn't exist out here because investors will bid up the price and will lower the return if the variance is too low. This line again represents the minimum variance portfolio. The efficient frontier is the highest return along this line for any given level of risk, of standard deviation here. And so I would not invest money where my cursor is right now, even though it's along the minimum variance frontier, because for the same level of risk over here, I can invest and get a higher return. So this is a rational investor would not invest down here. They would only invest along the efficient frontier. The global minimum variance portfolio is the portfolio that's right here. It's at the tip of the minimum variance frontier. It is the portfolio that has the lowest, the risky portfolio, I should say, that has the lowest amount of risk of variance. Right, so I'm going to draw, although I'm not good at it, I'm going to draw a little graph on our notes to describe the next part. So what we just saw was a graph with our expected returns, our expected returns along the y-axis, our standard deviation along the x-axis. We have the efficient frontier, goes like this, and then the dotted line makes up the rest of minimum variance frontier. And within here are the possibilities for all of our risky portfolios, and those risky portfolios include the portfolios that occur along these lines here, the dashed line and the solid line. And again, this is our efficient frontier. So when we create our complete portfolio, so our risky portfolio is going to be contained along this line if we did a good job of determining the weights. Okay, so it's going to be along this line. And then our risk-free assets down here, and that's our y-intercept. So the return we're going to choose for our risky portfolio is going to be the tangency point between the line that's created from the risk-free asset to the efficient frontier. So that will be our portfolio that we would choose. Okay? And then again, the level of risk aversion that a person has will determine where along this line, remember, if you remember back, it's the capital allocation line, where along this line someone's going to invest. So now we get into some weird math. The variance of a portfolio is equal to the variance, and then we've got a bunch of symbols in here, summation, the weight of each individual asset multiplied by the covariance of each individual asset. And I'm going to use matrix multiplication in Excel to demonstrate this. So I'm going to end this video now, and then the next video will actually take you through the steps here to calculate the best risky portfolio, and then the weight in the risky portfolio and the weight in the risk-free asset that an investor would choose based on their level of risk aversion. All right, and so that's the next video that's going to be out online. Again, let me know if you have any questions about any of these calculations, or need a better, or would like a better discussion, or have some questions about the discussion that goes along with these. All right, thank you.